Okay, so our next section is going to be 5.3, talking about diagonalization. So we've talked about eigenvalues and eigenvectors. Okay, we also talked about similar matrices just a little bit in the last section. We're going to use all this information to formulate another idea here about how to make matrices easier to work with and easier to do computations with, easier to do operations and the like. Okay, so first we need to understand what a diagonal matrix is. So a diagonal matrix is a square matrix with entries, with non-zero entries, I should say, only on the main diagonal. Okay? So we say a matrix, so let's look at a diagonal matrix, look at some interesting properties. So if I have a diagonal matrix D that looks like 2, 0, 0, -3. So I have 0, 2, and -3 on the diagonal. And the first thing to notice here about diagonal matrices, and the reason that they're so useful, is that if I take D squared, I am multiplying D times D. Okay, and when I multiply D times D, I'm going to go across and down. So 2 times 2 is 4 plus 0. So I get 4. Across and down again, 0 and 0 is going to be 0. Okay, 0 and 0 is going to be 0. And then second row, second column is going to be 0. And then -3 times 3 is 9. -3 squared gets us a positive 9. Okay. All right, so 4 and 9. Okay, that makes sense that D squared then is simply just the square of the positions on my diagonal here. Okay, sorry, I'm fidgeting with the camera, trying to make it as clear as possible here for you. So 4 and 9, then I just square the diagonal. So we'll see then that if I go to D cubed, well, I would get 2 cubed is 8, and -3 cubed would be a -27 with zeros elsewhere. So that's going to apply for any D to the K power. In this case, that's 2 to the K and -3 to the K power with zeros elsewhere. Okay, and so that's true for any diagonal matrix. So if I have a diagonal matrix D that simply has lambda 1 through n on the diagonal with zeros above and below, I know that raising that to the K power would give me lambda to the K power for each value lambda. Now, why did I write those as lambda? Because we know that for a triangular matrix, and a diagonal matrix is definitely a triangular matrix because I have zeros above and below. So it's actually upper triangular and lower triangular. So that's actually another way to define diagonal matrix, is to say a diagonal matrix is one that is both upper triangular and lower triangular. Okay, some mathematicians like that definition because we don't have to introduce a new thing. We're defining it based on previously defined terminology. Okay, but we can think of it either way. Okay. And so I wrote those as lambda because it's diagonal, which means it's triangular, which means that for a triangular matrix, the eigenvalues appear directly on the diagonal. Okay. Now, last time we talked about similar matrices. Okay, we touched on it just a little bit. And the reason we touch on it a little bit in 5.2 is to talk about it more in depth here in 5.3. So if I talk about similar matrices, what I'm looking at then is A is similar to B. Similar matrices. A is similar to B if there exists, that backwards Z means there exists, I'm using a little shorthand here, a matrix P that is invertible and A is equal to P inverse, P, B, P inverse. Or we can go the other way and say P inverse AP is equal to B. Okay. Now, our most interested, and the reason we like this is because the determinants, we can use those because the determinant of P inverse and P we know will make 1. So I know the determinants are equal, which means that the characteristic equations are equal if I do lambda minus lambda I on each side. If the characteristic equations are equal, they have the same eigenvalues. Okay. So similar matrices have the same eigenvalues. Okay, so if I'm looking at a diagonal matrix, the type of diagonal matrix I'm most interested in is the ones that are similar, that create a similar setup. Okay, so what I'm looking for then is diagonal matrices such that A is equal to PD P inverse, where P is invertible and D is diagonal. Okay, those are the things I am looking for. Those are the things I'm most interested in here. Okay, now if we consider, notice that the definition for similar does not require it to be diagonal. Okay, so you can have a similar matrix that's not diagonal. However, what we're most interested in are similar matrices that are diagonal because I can quickly determine the eigenvalues. Okay, and if I know the eigenvalues, I can use those to find the eigenvectors. Okay, so these two concepts, the eigenvalues and eigenvectors, go right along with diagonalizability. I know that's a tricky word. So if a matrix can be written this way, we say A is diagonalizable. Okay, A is diagonalizable, and if A is diagonalizable, then we can talk about, if we're talking about a matrix that's unknown, we're asking about its diagonalizability, which is, again, another long word. Okay. Now, let's look at a matrix here. So a matrix A. My matrix A is 7, 2, -4, and 1. Okay. I know I can find the eigenvalues of this matrix. Okay. So the eigenvalues of this matrix, I would take the determinant of A minus lambda I and set it equals 0. So A minus lambda I would be 7 minus lambda and 1 minus lambda on the diagonal, 2 and -4 for the other positions. Okay, so my determinant then would be 7 minus lambda times 1 minus lambda plus 8 equals 0. Okay, multiply this out. So I get 7 minus lambda minus 7 lambda plus lambda squared plus 8 is equal 0. Okay, keep simplifying. I've got lambda squared minus 8 lambda plus 15 is equal to 0. So I have lambda minus 3, lambda minus 5 equals 0. It factors that way. So I have my eigenvalues then are 3 and 5. Okay? Now, knowing what we know about an eigenvalue, we know an eigenvalue means that this is AX equals lambda x. Okay? So if I multiply lambda and x, I'm going to get AX. And what is AX? AX is a product of matrices. So to determine if this is diagonalizable, to find the diagonals, what I'm actually looking for then is the diagonal matrix to have the eigenvalues. Because I know if I multiply those eigenvalues by the vectors, they're going to multiply out to A. Okay? So if this is my D, then I can find P simply with the eigenvectors. Okay? So let's finish out that thought here. Okay, so I've got my two eigenvectors, 3 and 5. So A minus 3i. We're going to subtract 3 on the diagonal. So I'm going to get 4 and -2 with 2 and -4. Okay, which we can quickly row reduce to 1, 1. Sorry, 1, 1/2. Yeah, it looks better. 0 and 0, right? I would get the zeros by simply adding, and then I'll scale this by 4 to get me 1 and 1/2. So I have x1 is equal to -1/2 x2, and x2 is free. Okay, so we might write -1/2 1 as our vector, or we might prefer, in fact, we do prefer, to get rid of the fraction. So I'm going to have -1 and 2. Okay, so I'm going to go a minus 5i now. Okay, so we're going to go on to a minus 5i now. So I'm going to have 7 minus 5 is 2. 1 minus 5 is a -4. Okay, gets me 2 and -4. Okay, I quickly get that to 2, 2, 0, 0, which then I can scale to 1, 1, 0, and 0. So I have x1 is equal to -x2, and x2 is a free variable. So my vector then should be -1, 1. Okay, so I've got my two eigenvectors, I've got my eigenvalues, okay? So I know that if I multiply these vectors by these values, it will give me AX, okay? So my matrix P is exactly these eigenvectors. So -1, 2, and -1, 1, or my matrix D is exactly those eigenvalues, 3 and 5 on the diagonal, okay? And then P inverse, I can find using my methods for finding inverses, right? So I take the determinant. So what's the determinant of P? The determinant of P would be equal to -1 plus 2. So I get 1 for the determinant of P. That's going to make the computations easy. That's good. Okay, and so then find the inverse, right? We make the main diagonal negative. So it's going to be 1 and -1. And the off diagonal, said that backwards. I want to switch the main diagonal, which in this case gives me the same result. So I switch the main diagonal, switch A and D, and then make the off diagonal negative. So that's going to give me -2 and then a +1 for P inverse. Okay. Now it's important that we also recognize that we do not have to have a unique diagonal representation. Okay. There's no reason to expect that representation to be unique. There may, and in fact will, in almost every case. I don't want to say every because that's a big statement, but in almost every case, there'll be multiple representations for the diagonal. You can imagine there's no reason I had to write 3 and 5 in this order. Okay, I could switch those around, in which case I would switch the vectors P. And also I could have multiplied this by a negative, so I get a +1 there, go 1, -2, and 1, -1. Okay, so lots of different methods that you could do, and you'll notice that that's actually the inverse exactly. Okay, so there's multiple ways you could go about this diagonalization procedure, okay? But the important thing is you need the diagonals and you need the, you need the eigenvalues on the diagonal matrix and you need the eigenvectors to be your matrix P, okay? So let's look at a definition here. Okay, this is theorem 5, which is also called the diagonalization theorem. Okay, and that says an n by n matrix A is diagonalizable if and only if, remember the IFF is if and only if, the matrix A has n linearly independent eigenvectors. So remember those examples we did at the end of 5.2 where we have to determine how many eigenvectors there are. So if there are not enough eigenvectors, you don't have a diagonalizable matrix, okay? Further, A is equal to PDP inverse if and only if the columns of A the columns of P, all right, I got ahead of myself on my definition here, are linearly independent eigenvectors of A with D having diagonal entries of the corresponding eigenvalues. Okay? Because remember, AX is equal to lambda x because they are the eigenvalues and eigenvectors. Okay? So this gives us our diagonalization algorithm. It's like we had a row reduction algorithm, we're going to have a diagonalization algorithm. Okay? The diagonalization algorithm is going to be to find the eigenvalues. Okay, you can use that using whatever means you find the eigenvalues. Maybe they're given. Maybe the matrix is triangular, so you can quickly determine them. Maybe you have to solve the characteristic equation. Okay, some are a little harder than others. Some are easier than others. Find the eigenvalues by whatever means. 2, then you're going to find the corresponding eigenvectors. And 3, you construct P and D using 1 and 2. Okay, you could put a step 4 down here, which would say that you find P inverse by taking the inverse, but that's not really inherent to anything to do with diagonalization. We know how to find the inverse using other means of how we found the inverse, right? You can use your inverse algorithm where you augment it with the identity and row reduce accordingly. You can use the special formulas. You can use cofactor expansion, all sorts of things you can do to find the inverse, okay? So do whichever one works for you, okay? So let's look at some matrices here that we're going to try to diagonalize if we can. Okay. First matrix up here is going to be A, which is equal to 1, 3, 3 on the top row, -3, -5, -3, and 3, 3, 1 on the bottom row. Okay. So we're going to try to diagonalize this. We need to figure out the eigenvalues. Okay. So for this one, I'm going to tell you the characteristic equation. So the determinant of A minus lambda I is equal to negative lambda cubed minus 3 lambda squared plus 4. And I'm setting that equal to 0. Okay. Now use your favorite method for factoring. Okay. It's an online class. Use the internet. Use Wolfram. Okay. Use TI-89, whatever works for you on how to factor this. We're going to factor this. If you need help factoring, please get in touch with me. But we're just going to factor this here into lambda minus 1 and lambda plus 2 squared, okay, with a negative sign. So I can see then that the eigenvalues are lambda equals 1 and lambda equals -2. Okay, those are my eigenvalues. Okay, now you'll notice there's only 2 of them. And if this is going to be diagonalizable, I need 3 eigenvectors. So one of these better have a eigenspace that's 2-dimensional. Okay, well, let's take them one at a time. So I'm going to have A minus I for eigenvalue of 1. So I subtract 1, I get 0, -6, 0. Okay, then other places are unchanged. 3, 3, -3, -3, 3, 3. Okay. Use your favorite method for row reducing. I'm going to get 1, 0, and -1. 0, 1, 1, and then all zeros on the bottom row. Okay, so let's figure out what we had here, right? I needed negative copy of the first row and a positive copy of the second row, okay, to get me 0, okay, when I put all that together. Okay, I'm subtracting those, subtracting those, so forth. Okay, so I've got x1 is equal to a positive x3, x2 is equal to a negative x3, and x3 is a free variable. So my vector then is 1, -1, 1. Okay, so I didn't get 2 eigenvectors there, I just got the 1. Okay, so we're going to go to A plus 2i now. Okay, A plus 2i, I'm going to get 3, 3, 3, -3. -5 plus 3 is -3. -3, and 3, 3, 1 plus 2 is 3. Okay, so that's clearly a dependent relationship. Okay, that's much is very evident very quickly. Okay, so I can row reduce this. I can cancel off the bottom two rows. I'm going to get 1, 1, 1 along the top with zeros along the other two rows. Okay, so x1 is going to equal negative x2 minus x3. x2 is a free variable, and so is x3. So I do have two vectors here. And those two vectors are going to be for x2, negative 1, 1, 0, and for x3, negative 1, 0, and 1. So now I can use this to construct my eigenvalues and construct my diagonal matrix. Okay, so A is equal to PD P inverse. P is the eigenvectors, so 1, negative 1, 1, negative 1, 1, 0, negative 1, 0, 1. You can check that those are linearly independent if you need to, but the way they're constructed with the eigenvectors, they should be. And then my matrix D, sorry, I don't want to put that there. That's P. So my matrix D then has to be the eigenvalues in the same order. So I use the eigenvector here for lambda equals 1 first, so it has to be 1. And then my other two eigenvectors were negative 2. Okay. Now notice, remember I said that P and D did not have to be unique, right? I could rearrange these accordingly. But there is a corresponding P for each D. Okay, you could actually put the 1 in the middle, and then you would put the eigenvector for 1 in the middle of P. Okay, so you have to have the same order here, but that means that there are a number of arrangements that are still valid diagonalizations for this matrix. Okay. Now we can have easier cases, or maybe it's a triangular matrix. So I'm going to take a matrix B now. A matrix B is 3, negative 8, 1, 0, 0, 7, and 0, 0, negative 2. Okay. So as I look at this, this is a triangular matrix. Okay, clearly triangular. So since it's triangular, I know the eigenvalues right off. It's 3, 0, and negative 2 because they are what are on the diagonal. Okay. Now, depending on the question, maybe the question just asks you if it's possible to diagonalize it. Well, if you have as many eigenvalues as you do columns in your matrix, or rows for that matter, it's square. Right? Then you know that that is diagonalizable because that means you have that many eigenvectors. If you don't have that many eigenvectors, it's not diagonalizable. But every eigenvalue has to have an eigenvector. Okay, so looking back at A, we had to find the eigenvectors to know if it was diagonalizable. But for B, once I have the eigenvalues, I know it's diagonalizable already. Okay. Okay, now I would have to find those eigenvalues, but I could already write at least one version of D. I can say that D is equal to 3, 0, and negative 2 on the diagonal with zeros everywhere. Okay, and I could arrange those in any order, and then once I found the eigenvectors, I would then be able to determine P and P inverse for that matter. Okay. But if the question doesn't ask you to do the full process, then don't subject yourself to it, okay? Only make yourself do what you have to, okay? All right, so next we're going to go to a matrix C. Okay, so my matrix C here is going to have 5, 0, 0, 0, 0, 5, 0, 0, 1, 4, negative 3, and 0, negative 1, negative 2, 0, and negative 3. Okay, as I look at this, I can already see that the eigenvalues are 5 and negative 3. Okay, which is not enough to automatically determine what P or D might be. Okay, these have multiplicity too, so if I needed to write with respect to the multiplicities, I'd write them down again. So they may have two eigenvectors, not a guarantee, but they may have two eigenvectors. So let's attempt to find those. Okay, so I'm going to have C minus 5i. Okay, so I'm going to get all zeros on the first two rows because I'm going to subtract off their 5. Okay, minus 3 minus 5 is minus 8. Okay, when I row reduce that matrix, I get 1, 0, 8, 16, 0, 1, negative 4, and 4, negative 4. Both those are negative 4. And then my 0 rows, of course, have to go along the bottom. So I have a system of equations here that is x1 is equal to negative 8x3 minus 16x4. x2 is equal to 4x3 plus 4x4. x3 and x4 are free. So my eigenvectors, or my eigenspace with respect to the eigenvalue 5, would be the vectors negative 8, 4, 1, and 0. And then my b vector is going to be negative 16, 4, 0, and 1. Don't forget the 1s for the free variable position. Okay, so I've got my 2 for that. Okay, so let's go to the other eigenspace now. That would be the eigenspace for lambda equals negative 3. So we're going to do c plus 3i. Okay, so I'm going to get 8 and 8, 0 and 0 on the diagonal. Everything else stays the same. Above the diagonal was all zeros. Below was 0, 1, negative 1 going down. And 4, negative 2 going down there, and 0 there. So there's that. Row reduce that. Use your favorite method for row reducing. Okay. Hey, this one maybe looks a little strange because it's very sparse. It's all zeros here. So x1 is equal to 0, x2 is equal to 0, but then x3 and x4 are free variables. So my vectors are easy to write down. They're 0, 0, 1, 0, and 0, 0, 0, 1. Okay? So I've got my 4 vectors here. So P, negative 8, 4, 1, 0, negative 16, 4, 0, 1 that I wrote down back before. 0, 0, 1, 0, 0, 0, 0, 1. D then, okay, I use the eigenvectors from E5, from the eigenspace for 5. So I have to go 5 and 5, and then negative 3 and negative 3. Okay, and then use whatever means you like for finding P inverse if you need P inverse. But I know this is P, I know this is D, and I know then that PDP inverse would be equal to A. So A is diagonalizable. Okay, but if you don't have enough eigenvalues or you don't have enough eigenvectors, then you may not have something that is diagonalizable. Okay, so let's look at a simple one here. I'm going to have a matrix A. My matrix A is equal to 1, 1, 0, 1. Okay, it's diagonalizable, so clearly this has lambda equals 1 with multiplicity 2. Okay, so if I do A minus I, I'm going to get 0, 1, 0, 0, which would mean that x1 is equal to x1. It's the free variable, no pivot in the first column. And x2 would have to be 0, which corresponds to the vector 1, 0, but that's the only vector I have. Okay, so I only have one eigenvector. So I do not have enough eigenvectors in order to diagonalize this matrix. Okay, you have to have as many eigenvectors as you do dimensions in the original matrix. Okay. So then one more theorem here that we're going to talk about, or actually 2 more theorems. One that I said, but we're going to write it down as a theorem, and then theorem 7, it's a little longer. So theorem 6 I said, but it's a pretty short theorem. It says that an n by n matrix with n distinct, so notice it's distinct, so I don't have any repeated, I don't have any extra multiplicities. in distinct eigenvalues is diagonalizable. Okay, I have to have enough eigenvalues in order to be diagonalizable. Okay, I have to have enough eigenvectors, and if I have enough eigenvalues, then I know I have enough eigenvectors. Okay, now theorem 7, I'm not going to write out because it's a little long. Okay, I'm going to project it up here for you. Okay, so theorem 7 says that, sorry, I try to get a nice picture of it here for you. I get the right sort of shading on it so that it's nice and visible for you. Sorry, I had this configured earlier, but then I moved the camera around for, there we go, that looks nice. So an n by n matrix has distinct eigenvalues, 1 through p, lambda 1 through p. So the dimension of the eigenspace for lambda k is less than or equal to its multiplicity. So you can never have more eigenvectors than you have eigenvalues multiplicity. So if you have a multiplicity of 2, you can't have more than 2 eigenvectors. You could have less, but you can't have more. Okay? It's diagonalizable only if the sum of the dimensions of the eigenspaces equals n. So you have to have enough eigenvectors. That's basically what it says here. So if you just want to write that down, that's really what we're saying. Okay? The other thing is that once you have enough eigenvectors, that actually is a basis for the columns of A, okay, which gives you a basis for n. Okay, so there's a lot of words there. Feel free to write them down, pause it, look at them, do what you need to do. Okay, but the big thing here is you have to have enough eigenvectors in order to get a diagonalizable matrix. If you don't have enough eigenvectors, then your matrix is not diagonalizable. Okay, that is theorem 7. Okay, the other important thing to remember is that you can read these backwards. Okay, so if I have P is equal to 1, 2, negative 1 with 3, 1, 1, and negative 2, 3, 3, and D is equal to 1, 2, 3, zeros elsewhere. Okay, I can use this to find A. I can use this to find information about A. I know A is equal to PDP inverse. So I know then that the eigenvalues of A are simply those entries on the diagonal. And I know that the corresponding eigenvectors can be read from that as well. So the eigenvector that goes with lambda equals 1 would be 1, 3, negative 2. With lambda equals 2 would be 2, 1, 3. And with lambda equals 3 would be negative 1, 1, 3. So you can also read these theorems backwards, all these properties. You can be given the end result and work backwards to the original matrix A. I could type these in and find A. Okay, simply multiply. If you know P and D, all you have to do is multiply PD and P inverse. Okay. If we find out that P inverse doesn't exist, that tells us something as well. It tells us A, right, did not actually have those eigenvalues. A was not diagonalizable. Okay. If we find that P inverse does not exist because it has to have that specific relationship with the eigenvalues. Okay. So with no 0 eigenvalue, that tells you something as well. If 0 is an eigenvalue over here, that tells you the columns of A were dependent. Remember that property from the last section. So if you get a D that has 0 on the diagonal, you know something then about A. You know that A was not, the columns of A were not independent. Okay. And remember also that D to a power, we simply have to multiply. That was the very first thing in this section. I know it's been a while. You watch all the way to the end of the video and you forget. That's where we talked about. That's why diagonal matrices are important or useful, is that if you have a diagonal matrix, you can raise it to a power by merely multiplying accordingly. So if I do A to a power, okay, so the observation there, right, if I have A to the K power, and I know A is diagonalizable, what that means is I can bring that diagonal K into the D and take care of that K power, okay? PDP inverse then will not be an issue because all of my copies of P and P inverse will wind up canceling and making the identity, okay? It will expand and then they'll all collapse on each other, leaving us with just the K power on the diagonal. So if you need A to the K and you know D, you can compute A to the K much easier than having to multiply out. A here is going to be pretty messy if you look back at that previous example with P and D. So you can use that property as well to help you solve some problems and solve some properties as it pertains to matrices. Okay, So we have one more section in chapter 5. That is section 5.5, where we will talk just a little bit about complex eigenvalues. That's really our touch on complexity. Okay, so we don't do just a ton with it, but it is here a little bit. We'll touch on that in 5.5. Okay, and then we will go to chapter 6, and we just have those first 4 sections of chapter 6, and that should conclude our semester. Again, if you have any questions, please contact me. I'm happy to help. Stop by office hours. Make sure you're staying up to date with homework, quizzes, and everything in both my math lab and D2L. And I'll see you again for the next video.